equal to n over n plus 1 is the infinite series of this. So as I told you, the difference between a series and a sequence. Now a sequence has comma in between, but with a series it has plus that you are summing them up. So please, you should know that. Now let's consider this: x1 be equal to a1, x2 be equal to a1 plus a2, x3 be equal to a1 plus a2 plus a3, and sn. So you are summing them up to an. Note that x1, x2 and xn are what? Sequence of numbers called partial sum. So when you combined s1, s2, s3, we call them partial sum. Note that. So now, definition: for any infinite series, the nth term, that's the nth partial fraction or the partial sum, is given by this. So you are just adding them. If the sequence of the partial sum converges to s, the sequence converges or the series converges. This means that when the sequence converges, the series also converges. So you should know that. So when you solve and the sequence converges, the series also converges. So when they give you, for us to know whether a sequence converge or diverge, let's see. So you find the limit as n approaches to infinity of the sequence or of the function given to you. If the sequence sn diverge, the sequence also, so it's the vice versa. So if the sequence also diverges, the series also diverges. So now let's take a special series, that's the geometric series. As you know, mostly we've done this more over and over. So what you need to know is, with the geometric series, it's in the form of this. So it's like arn minus 1. So there's a condition for r. So let's see that. So for us to determine whether a series converge or diverge, we will only relate to the r. So let's see this. So note this: the geometric series converges if and only r is less than 1. So when you solve and r is less than 1, it will converge. Let me come again. When you solve and r is less than 1, it converges. So as you can see, this is the sum of series, that is a over 1 minus r, and r is less than 1. So if r is less than 1, the series converges. But if r is greater than or equal to 1, the series diverges. So what you need to know is, take note of this, and also take note of this. That's the main thing we should take note of. Please, if you have any question, you can ask by commenting in the box so that I can reply you. Let's take this question. From the first form, it can be shown that the partial fraction is, you see, let's take this, the sum of the nth term, that's the sum of series, that is a into bracket n minus 1 minus r exponent n over 1 minus r, where r is less than 1, and if r is less than 1, it converges. You should know that. And if r is greater than or equal to 1, it diverges. A is the first term. So let's take this example. Determine whether the series converges or diverges. So with this, for us to determine whether the series converges or diverges and also find its sum, it all relates to the r, which is this, the r. So in this sequence, you know this become our a, r exponent n minus 1. So r is down 2 over 3. And when we take 2 over 3, we're going to get 0.67, which is less than 1. Therefore, this series will what? Converge. That is, from the above series, r is 2 over 3 and r is less than 1. Therefore, the series converges. And for us to find the sum to infinity, you know that the first term over 1 minus r, which you know the first term to be what? A here, and the r, that is the common ratio, to be 2 over 3, which is 0.667. So you just put inside the equation, which will give you 6. that the sum of this one is 6. So this is as simple as that. So this is one of the special series. Now let's move on to the test. I love this test. With this test, P-series test, if you understand this P-series test, you can solve most of the test. You can just look through the function and just predict that this will converge or diverge. So let's take the condition for the P-series. Now with a P-series is a series of the form that is 1 over n exponent p. So the p can take any natural number, that is 1 exponent p, this one. So the p, so what is important is the p. So now the series P series converges for p is what? Greater than 1. So if p is greater than 1, it will converge, and if p is less than or equal to 1, it diverges. This is different from the geometric series. That one is different. When r is less than 1, it converge, and when r is greater than 1, it diverge. This is a series. So what I want you to know is take note of this. When you get a function like this and p is less than or equal to 1, it diverges, and p being greater than 1, it will converge. We'll surely take example. Now the p test is applied in the comparison test. Now the comparison test is just comparing, that is bn and an. So suppose we have two series, that is sum of an and bn with an. So bn is greater than or equal to 0 for all n and an. So I want you to take note of this. It's one of the base thing we need to know. So bn is greater than or equal to 0 for all n, and with an is less than or equal to bn. So it means that an is less than bn is greater than an. So if bn converges, then an also converges. So we only determine with the comparison test, we compare them to know. So if one, for the convergence, if bn converge, an also converge, but with the divergence you check on what? The an. So with the convergence you check bn, and with the divergence you check what? The an. Let's take example. Now with this, what I told you about the P series is that it's very simple with using the P series, as I told you. Now this is 2. You can just look through your eyes and just say that this function will what? Converge, because p is 2, and if p is greater than 1, it's what? Converges. So simple. You can just do it just looking at the function. That's what I told you. Now with here, this question, p will what? Diverge, because this will be n exponent 1 over 2, and as you know, half is less than 1. Therefore if p is less than 1, it will what? Diverge. As simple as that. So with the P series, it can be applied in ratio, comparison, root, and all. Now let's take another example. With this, you can just check that this series will what? Converge. Simple, because p here is greater than what? 1. It will converge. Simple. So you can just determine if the series converge or diverge. This series will converge. Why? It's a P series, and if p is what? Greater than 1, it will what? Converge. Please, if you have any question, you can just comment so that I can reply you on that. Thank you. Now the limit comparison test, we are going to compare. Suppose we have two series an and bn with an because, so this is like similar to the comparison test, but with this you take the limit, and if c is positive and c is what? Greater than 0 and is finite, it either converge, or with this one it's a condition. It comes with a condition. So with this, it comes with a condition. So when they ask you determine if the series converge or diverge, Now 1 over 2n, so pick bn. So you need to know this whole thing is your an and your bn, so you take the limit of an over bn. So you have you're going to multiply, because this whole thing is your an, so an over bn, and when you reciprocate this, you're going to get this. And when you find the limit as n approaches to infinity, you're going to get 1, because this will tend to 0 0 0 0, and 1 which will be 1 over 1, which will give you 1 is greater than 0, therefore it is positive. So by the limit comparison test, both series converge since it's positive. As I said, the limit comparison test is somehow, it has conditions. That is, it has conditions. Yes. Now let's go to the alternating series test. The alternating and the harmonic move together. So with the alternating, it's in a form of this. Take note of this, and it's in the form of this. So suppose that we have a series which is an. Either an is equal to negative, that's 1 exponent n, or negative n plus negative n, that's exponent n plus 1, that's bn, where bn is what, greater than or equal to 0 for all n. Then when you take the limit as n approaches to infinity and is equal to 0, then bn is decreasing sequence, then the series will converge. So what you need to know, that when you get a question in this form, in an alternating form, it converges. We are going to talk about harmonic. It's the vice versa of harmonic. When you get in the form of this form, that is in the form of this, just the series will converge. So let's take the harmonic. The harmonic is the opposite of the alternating. So with this, it's 1 over n. Are you getting it? And it's harmonic. And harmonic series, they diverge. So when you get a question like this, but note, when this is having an exponent, maybe a number, maybe n exponent 3, maybe 3 here, this is no more harmonic, it becomes p-series. So this series will what? Converge. But when there's no exponent here, it is harmonic, therefore it will what? Diverge. So let's do this. As you can see, this series, you can just look through and tell me that this series will converge. Now it contains two conditions. We have the alternating here and harmonic, but the alternating precedes the harmonic, so therefore the series will what? Converge. Just seeing it, you don't need to do anything. As you know that you've seen alternating, it just converges. The absolute convergence. A series an is called the absolute convergent if the absolute of an is convergent. If an is convergent, then the absolute of an is convergent. We call it series conditionally. This is conditionally, well, it's like the limit comparison test conditionally. Yeah, so note, if an is absolutely convergent, then it is convergent. So with this you seeing that this is an alternating. You see, with the test, what the wonderful about this test is that you can combine them, they help each other or one another. So with this, you can just tell them that this converge because it's alternating. You don't need to take the how something like that. When you see this, you determine whether it will converge. Let's see the solution. So it's alternating harmonic. What I said, alternating. So you know that it's alternating. Simple. This series will converge. So what you need to know is that you know the condition for the alternating and you know the condition for harmonic. The P series, you are good to go. The ratio test. When you talk about ratio, it's something over something, right? Maybe A over B. So when you talk about ratio test, it is suppose we have a series an defined as L, that's the limit, is equal to the limit as n approaches to infinity. So this is an plus 1 and an. So normally when they give you the series, you need to find, they'll give you the an. So you need to find the an plus 1. What you need to do is wherever you see n, you replace it by n plus 1. Now the condition for this is if L, that's the limit, is less than 1, the series converge. And if L is greater than 1, it's diverge. And if L is equal to 1, the ratio test is inconclusive. Please don't confuse yourself with the P test. With the P test, if P is greater than 1, it will converge. But with this, with the ratio test, if L is greater than 1, it diverges. You should know the difference. And with the ratio test, if maybe you have a question and you want to try and use ratio test and you get L should be equal to 1, it means that you cannot use ratio test. You need to use other test. Maybe whether you can use other tests, maybe comparison or anything. So that's what I want to tell you. Now let's find this. Determine the series. So with this, they say that determine if the following series are converge or diverge. So with this is an. So what you need to do is you find an plus 1. That's wherever you see n, you place what? N plus 1, as you can see. So you find n plus 1. This is n plus 1. So wherever you see n, this is a. So it will be n plus 1 over a. And that's the limit as what? N plus 1 times 1 over a n. And the series will converge. But let me show you something. There's something interesting about this series. There's alternating series here. So me rather, if you give me this question, or this question is to be solved in MCQ, and they ask whether this series converge or diverges, what you need to know that you know alternating, so you can bring it to the ratio test to find the alternating, and you can just do it in a simple way, because this will definitely converge. That's all. But you should know that with the ratio test, it will be an plus 1 over an, and you find the limit as n approaches to infinity. And you should know that if L is, when you find the limit is L, the result of the limit, if L is less than 1, it will converge, and if L is greater than 1, it will diverge. And if L is equal to 1, the ratio test is inconclusive. Now let's look at this. So they had 10 over 16, which is less than 1, and the ratio test converge. Simple, because there's alternating inside. Simple to converge, as simple as that. This is for MCQ. The root test. This root test, when you talk about root, you're taking the square root, the nth root. This is not the square root, so the nth root, that's 1 over n. Suppose we have the series an defined, and L is a limit as n approaches to infinity. The nth root an is equal to limit, that's the limit as n approaches to infinity, an, that's n minus n over 1. Sure. So with this, it's the same approach. That is, the root test use the same condition for the ratio test. If L is less than 1, before, when you find the limit of this, so you are going to, they'll give you an, that one you're not going to find an plus 1, and just find the nth root of it. And if L is less than 1, it will converge, and if it's greater than 1, it's what? Diverge. And if this diverge, and if L is equal to 1, it means that you cannot use the ratio test. Note that. So with this, you have this is an. So what you need to take the nth root. So they took the nth root, 1 over 9 of all the absolute values. So you're going to multiply this by this. When you multiply this is going to cancel this, and when you multiply this by this, you're going to get 1 over n, and the 2n will cancel the n, which will give you infinity over 9 is infinity, and infinity is greater than 1, which means that it will diverge. Simple as that. The integral test. With the integral test, well, I'll not go deeply with the integral test because I have a previous video on the integral test, how to use the integral test to find whether a series converge or diverge. But let me brief you on this integral test. So with the integral test, supposing that f of x is continuous. When you talk about continuous, it is finite, it exists, and the other two sides are equal or something, yes, something like that, yeah, and positive and decreasing function on the interval. This is a closed interval k, and this is an open interval to infinity. Then that of fn is an. Then when they give an improper integral, this is an improper integral. So what you need to do is you're going to, if the integral of infinity over k f of x, the x is convergent, so an also is convergent. So when they give it to you, you're going to find the integral of the an, and if it's this, when you place it by this and it's convergent, this also is convergent. If it's divergent, that also is divergent. So let's take an example of it. So this is the question, this an. So you're going to take the integral, that's the improper integral. That's the first principle. You have two type of you have the is it the integrand and the yes. So with this, you're going to replace this with an alphabet. As I told you, I've done a previous video on this. Yes, previous video on this. So you can just go to my YouTube channel. You're on my YouTube channel. You can just go through my videos and you see this. I just brief more on this. Yes, I brief more on this. Yes, so all this I have brief on that on my YouTube channel. So check my YouTube video and check that. Thank you very much for watching my video. Yes, thank you very much for watching my video.